Shift registers. A flip-flop can store only one bit of data, that is a 0 or a 1, and it is referred to as a single bit register. When more bits of data are to be stored, then a number of flip-flops are to be used. A register is a set of flip-flops which is used to store binary data. The storage capacity of a register is the number of bits of digital data which it can retain. Loading a register means setting or resetting the individual flip-flops, that is, inputting data into the register so that their states correspond to the bits of data to be stored. Loading can be done in serial or parallel fashion. In serial loading, data is transferred into the register in serial form, that is, one bit at a time, whereas in parallel loading, the data is transferred into the register in parallel form, meaning that all the flip-flops are triggered into their new states at the same time. Parallel input requires that the set or reset controls of every flip-flops to be accessible. If a register is capable of shifting bits either towards the right hand side or towards left hand side is known as shift register. That is, the bits are shifting in a register. An n-bit shift register contains n flip-flops, where each flip-flop will be storing only one bit. The different types of shift registers based on applying inputs and accessing of outputs are serial in serial out shift register, serial in parallel out shift register, parallel in serial out shift register, parallel in parallel out shift register. Shift registers are a type of logic circuits which are closely related to counters. The shift registers are used basically for the storage and transfer of digital data. The basic difference between a shift register and a counter is that a shift register has no specified sequence of states except in very certain specialized applications, whereas a counter has a specified sequence of states. A shift register is a very important digital building block. It has innumerable applications. Registers are often used to momentarily store binary information appearing at the output of an encoding matrix. I may use to accept input data from an alphanumeric keyboard and then present the data at the input of a microprocessor chip. A number of flip-flops connected together such that data may be shifted into and shifted out of them is called a shift register. Data may be shifted into or out of the register either in serial form or in parallel form, and hence the four basic types. Now we can see each of the types in detail. The first one is called serial out shift register or SISO. This type of shift register accepts data serially one and also outputs data serially. The logic diagram of a 4-bit serial out shift register is shown in the figure with 4 stages, that is 4 flip-flops. The register can store up to 4 bits of data. Serial data is each flip-flop at the positive going edge of each clock pulse. The bit that was previously stored by the first flip-flop is then transferred to the second flip-flop. The bit that was stored by the second flip-flop is transferred to the third flip-flop and so on. The bit that was stored by the last flip-flop is shifted out. A shift register can also be constructed by using JK flip-flops or SR flip-flops as shown in the figure. The data is applied as the J or S input of the first flip-flop. The complement of this is fed to the K or R terminal of the first flip-flop. The output of the first flip-flop is then connected to the J or S input of the second flip-flop and the Q output of the second flip-flop to J or S input of the third flip-flop, and so on. Also, Q complement is connected to K2 or R2 and Q2 complement is connected to K3 or R3, and so on. Serial in, parallel out, shift register. The logic diagram and the logic symbol of a 4-bit serial in, parallel out, shift register. In this type of registers, the data bits are entered into the register serially, but the data stored in the register is still shifted out in parallel form. Once the data bits are stored, each bit appears on its respective output line and all bits are available simultaneously, rather than on a bit by bit basis as with the serial output. The serial in, parallel out shift register can be used as serial in, serial out shift register if the output is taken from the Q terminal of the last flip-flop. Parallel in, parallel out shift register. In parallel in, parallel out shift register, the data is entered into the register in parallel form and also the data is taken out of the register in parallel form. Immediately following the simultaneous entry of all data bits, the bits appear on the parallel outputs. The figure shows a 4-bit parallel in, parallel out shift register using D flip-flops. The data is applied to the D input terminals of the flip-flops. When a clock pulse is applied at the positive going edge of that pulse, the D input is shifted to the Q outputs of the flip-flops. The register now stores the data. The stored data is available instantaneously for shifting out in parallel fashion. Parallel in, serial out shift register. For a parallel in, serial out shift register, the data bits are entered simultaneously into their respective stages on parallel lines rather than on a bit by bit basis on one line as with the serial data inputs. But the data bits are transferred out of the register serially, that is on a bit by bit basis over a single line. The figure shows a 4-bit parallel in, serial out shift register using D flip-flops. There are 4 data lines D0, D1, D2, D3 through which the data is entered into the register in parallel form. The signal shift or load bar allows the data to enter in parallel form into the register and the data to be shifted out of serially from the terminal Q4. When shift or load bar line is high, the gates G2, G3 and G4 are disabled, but the gates G5, G6, G7 are enabled, allowing the data bits to shift right from one stage to the next. When the shifter load bar line is low, the gates G5, G6 and G7 are disabled, whereas the gates G2, G3 and G4 are enabled, allowing the data input to appear at the D inputs of the respective flip-flops. When a clock pulse is applied, these data bits are shifted to the Q output terminals of the flip-flops, and therefore data is inputted in one step. The OR gate allows either the normal shifting operation or the parallel data entry depending on which AND gates are enabled by the load or shift input. Bidirectional shift register. A bidirectional shift register is one in which the data bits can be shifted from left to right or from right to left. The figure shows the logic diagram of a 4-bit serial in, serial out bidirectional, that is shift left, shift right, shift registers. The right or left bar is the mode signal. When the right or left complement is a 1, that is high, the logic circuit works as a shift right shift register. When the signal is low, it works as a shift left shift register. The bidirectional operation is achieved by using the mode signal and 2 AND gates and 1 OR gate for each stage as shown in the figure. A high on the right or left control input enables the AND gates G1, G2, G3 and G4 and disables the AND gates G5, G6, G7 and G8. And the state of the Q output of each flip-flop is passed through the gate to the D input of the following flip-flops. When a clock pulse occurs, the data bits are then effectively shifted one place to the right. A low on the right or left bar control input enables the AND gates G5, G6, G7 and G8 and disables the AND gates G1, G2, G3 and G4. And the Q output of each flip-flop is then passed to the D input of the preceding flip-flop. When a clock pulse occurs, the data bits are then effectively shifted one place to the left. Hence, the circuit works as a bidirectional shift register. Universal shift registers. A register capable of shifting in one direction only is a unidirectional shift register. One that can shift in both directions is a bidirectional shift register. If the register has both shift and parallel load capacities, it is referred to as a universal shift register. So, a universal shift register is a bidirectional register whose input can be either in serial form or in parallel form, and whose output also can be either in serial form or in parallel form. The most generous shift register has the following capabilities. First one, a clear control to clear the register to 0. Second one, a clock input to synchronize the operations. Third one, a shift right control to enable the shift right operation and serial input and output lines associated with the shift right. A shift left control to enable the shift left operation and the serial input and output lines associated with the shift left. A parallel load control to enable a parallel transfer and N input lines associated with the parallel transfer. Sixth one, N parallel output lines. Then seventh one, a control state that leaves the information in the register unchanged in the presence of the clock. A universal shift register can be realized by using multiplexers. The figure shows the logic diagram of a 4-bit universal shift register that has all capabilities listed above. It consists of 4 D flip-flops and 4 multiplexers or MUX. The 4 multiplexers have 2 common selection inputs S1 and S0. Input 0 in each multiplexer is selected when S1 S0 is equal to 0 0. Input 1 is selected when S1 S0 is equal to 0 1. And input 2 is selected when S1 S0 equal to 1 0. And input 3 is selected when S1 S0 equal to 1 1. The selection input control the mode of operation of the register according to the function entries given in the table. When S1, S0 equal to 0, the present value of the register is applied to the D input of the flip-flops. This condition forms a path from the output of each flip-flop into the input of same flip-flop. The next clock edge transfers into each flip-flop the binary value it held previously, and no change of state occurs. When S1, S0 equal to 0, 1, terminal 1 of MUX input have a path to the D inputs of the flip-flops. This causes a shift right operation with serial input transferred into the flip-flop FF4. When S1, S0 equal to 1, 0, a shift left operation result with other serial input going into the flip-flop FF1 or the first one. Finally, when S1, S0 equal to 1, 1, the binary information on the parallel input lines is transferred into the register simultaneously during the next clock edge.